In this lesson, I'll show you how to use the chain rule with partial derivatives. We'll start with two separate cases on where you can use the chain rule with partial derivatives. Starting with case 1, we have to find the partial derivative via the chain rule for our function f of xy is equal to the following, where x is equal to t squared and y is equal to 5t. Notice that x is equal to an expression in terms of t, and so is y. So in case number 1, we deal with functions where x and y are in terms of one other variable, in our case t. So to find the partial derivative, I'll represent it as the partial derivative of our function, let's call it z, with respect to t. We will find the partial derivative with respect to x, and then we'll multiply by the derivative of this equation with respect to t. And that's represented right here. So the partial derivative of our function z with respect to x, let's go ahead and do that. We have 5 times 2x, notice that this power 2 is being multiplied now to the 5, times y, which is a constant, minus 3y is a constant, and the derivative of sine is cosine. Cosine x, the derivative of x is 1, so we multiply this by 1, but we don't need to show that. Now, according to this, we now multiply it by the derivative of this equation with respect to t. And the derivative of this equation is 2 times t. Plus, now we will take the partial derivative of this with respect to y, then multiply by the derivative of y with respect to t. So the partial derivative of this expression is 5x squared, and the derivative of y is 1, minus 3 sine x, that part is all constant, and this y is with what we're concerned about, and the derivative of that is 1. So we have this expression now multiplied to the derivative of that, which is 5. So let's clean this up. We have the partial derivative of our function with respect to t. This becomes 10. 5 times 2 is 10. And we can replace x with what it actually is equal to. It's t squared. Y is equal to 5t. So we can multiply these two later. Minus 3 times 5t cosine t squared. I'll put this in square brackets because it's being multiplied to 2 times t. Plus, and we treat this the same way, 5x is t squared to the power of 2. That becomes t to the power of 4 eventually, minus 3 sine t squared multiplied to 5. Of course, you can expand this further, but what you see is good enough. In case number 2, where we use the chain rule, is when x and y are in terms of two variables. Notice that here we have st and here we have 5t minus 3s. So our function is z, and it's equal to the following. We need to find now the partial derivative with respect to s and then with respect to t. So this is more work. We'll start with the partial derivative with respect to s. And we'll take the derivative now with respect to x and then s for this equation. Let's go ahead and do that. We have 10y plus 5y squared ex. And we will multiply this now to the derivative of this with respect to s. We end up with, we have dx over ds is, this becomes simply t, because remember it's with respect to s, and t's are constant. Once again, we now add, and we take the partial derivative of this with respect to y. We should end up with 10x plus 10y, because 2 times 5 is 10, e to the power of x. And we'll multiply this to the derivative of that with respect to s. dy over ds is, that becomes 0, and this becomes minus 3. So if we clean this up, you should have an expression that looks nice and neat like what I'm writing. So now what you can do is substitute wherever you see a y with this expression, wherever you see an x with this expression. And this is what you should have as your final partial derivative using the chain rule. 10 times 5t minus 3s plus, and I'll put this in square brackets because eventually we need to multiply by this factor t, 5 times 5t minus 3s raised to the power of 2 e to the power of st, close the bracket, t, minus 3 bracket 10 st plus 10 5t minus 3s e raised to the power of st. Now, of course, they're expecting us to find the partial derivative for the function with respect to t, but it's the same process as before. Now, if you would like to see this in action, I do have a question in part 2 of this series, and this is what we'll be covering. We'll hope to see you soon.